everyone, this is Kex Next, and today I'm going to go over some tips and tricks related to radial animation inside of Houdini. I think this is a very broad topic with a lot of applications in motion graphics especially, and FX work, and it's something that I struggled with when I was learning Houdini. So this is going to be a little bit more of a relaxed tutorial, so you can follow along if you'd like to, but let's go ahead and get into it. So I'm going to use a pineapple for demonstration purposes, but you can use whatever you want. But I'm going to go ahead and create a circle. All right, so we have our circle, and we actually don't need the geometry, so I'm going to put down an add node, which is kind of ironic because we're going to be subtracting the geometry, I guess. But yeah, we just want to delete the geometry but keep the points, right? And at this point, I do want to bring something up really quickly. And that is the point numbers. So the way the circle node generates a circle, it gives you these nice points that increase around the circle. The point numbers do. So you go from 0 to 11 because there's 12 points, right? We can change this or whatever. This is all fine and dandy, but what if you're given like packed geometry and you have packed primitives and the point numbers are all crazy and messed up, right? So now I just messed them up with this randomized sort node. So we're getting 8, 10, 2, 4. They're all crazy. They're all messed up, right? We don't want that. So how do we actually get them back algorithmically, right? So what we can do is calculate polar coordinates. So if you remember back to high school math, the unit circle, right? The unit circle is a circle plotted on a polar grid. And a polar grid is much like a XY grid, but instead of having X and Y values, you have radius and theta values. So to get a location on a polar grid, you have a radius, which is how far from the center you are, and a theta, which is where around the circle you are. So you can say radius of 2 at 19 pi over 12. You're right here, right? So it's just another coordinate system, right? Well, we have Cartesian coordinates. We don't have polar coordinates. But there's actually a way to convert between them with functions, and we don't need the radius for this tutorial, at least. I mean, this is how you would calculate it if you do need it, but we need theta. And so to get theta, we take the arctangent of y over x. Well, luckily in Houdini, it actually comes with some functions for that. So if we put down a point wrangle, start coding in some VEX, we can say, make a new float value called theta. It's going to be equal to a tan. And this is just the arctangent, but in Houdini you can get a tan 2, which is the arctangent of y over x. You just have to provide it the arguments, so that's pretty handy. So the arctangent, the a tan 2 of at p dot y, right, the y over the x at p dot x. And this might change depending on like what plane your circle is on, and you might have to rotate your circle to be on a specific plane for this, but for mine it's literally already on y and x. Okay, so how do we know that this is working, right? Or what this is doing? Well, I'm going to write this out to an attribute here. F at theta is equal to theta. And bring up our attributes down here. What we would expect it to be doing, right, is creating an attribute from this first point over here, going from 0 all the way around the circle to 2 pi, right? Because if we remember our unit circle, we get 0, pi is over here, all the way around. This is technically 2 pi for one full revolution. That's how the unit circle works. So what we would expect is it going from 0 to 2 pi all the way around, right? But if we look at our attributes down here, we have some negative values. And what it's doing instead is it is like 0 centered. So it's going from 0 to pi here, but then 0 to negative pi here. That's not what we want. So to correct that, we just have to write a little if statement here. We're going to say if theta is less than 0, right? If it's negative, we're going to set theta equal to 2 times pi. And to get pi, you just do $capital Pi is the H script expression there to get pi in Houdini. We're going to do 2 pi plus theta, right? Because we're adding a negative value. So what that's going to do is give us the theta continuation. So it's going to go from 0 to pi, and then it's going to continue on to 2 pi. And we can actually visualize that if we drop down a color node here, and we can do ramp from attribute, and the attribute is theta, and we'll do white to red. And just so that you folks at home over there on YouTube can see, I'm going to put down a wrangle here and say I at GL sphere points is equal to 1. This is an attribute that you can give stuff inside of Houdini that gives it GL spheres where you don't have to like do a copy to points node. So it's kind of handy for visualization. Okay, but this is, and also this color ramp is going from 0 to 1, but we know this should be from 0 to 2 pi. So we just have to type in here 2 pi. Okay. So we have exactly what we need. And this is like the base of the effect. So this is like just something that you can use, we can use it for shading purposes. So color, for, creating a bias value, for animation, for whatever, this is a good stopping point, I think. But if you want to keep going, I'm going to show how to make this little pineapple animation here and how you can animate this value. Create kind of like a looping animation for, I guess, motion graphics purposes. So I'm going to create a new point wrangle, right? And as a matter of fact, I'd like to plug this into there so we can see it better. Oh, and before I get into this very quickly, I forgot that you can, so since we have this theta value now, you can actually sort the points now by an attribute, that attribute being theta, and you can see now we actually have our point numbers back. So 0, 1, 2, 3, 4, all the way around. This will work for everything, completely procedural, very cool. I can increase this, number of points and you get the correct point numbers. So I want to show that before I move on. That was a very important thing that I forgot to mention. So I'm going to delete those now because we don't need those. I'm going to show how to animate these. So I'm going to make this node pink, call it animation, and let's go ahead and get started. Okay, so first things first, we need a value that kind of goes around this circle. If this is kind of an easier way to think about it, but if you want to think about it as like a number line, we need a value that goes from 0 to 2 pi, right, over a certain amount of time, and then restarts at 0. So 0 to 2 pi, 0 to 2 pi, 0 to 2 pi, right? So how do we do that? Well, we can generate a value based off of the current frame number. We need a few things first. I'm going to create a new integer attribute called dir for duration, and this is going to be the amount of time that it takes for this value to make its way all the way around the circle to so 1 revolution is how long this will be. And I'm going to make a new integer parameter here called duration, and this will be in frames. So I'm going to go ahead and click this to get the attribute to appear, and let's do 35 frames for now, which will be enough to see kind of if this is working. I'm going to make another attribute. It's going to be a float. This is going to be the value that spins around the circle. Okay, so first we need a value based on the current frame, right? So if we set this equal to @frame, this is an attribute that Houdini provides that gives you the frame number or the current frame number inside of this wrangle, right? So this is very handy. But what this will do, this won't create a looping animation. It will just give you the frame number, right? But let's say we want it to go from 1 to our duration, so 1 to 35, and then the next frame will be 1 again. So it's going to start over. We're going to use a modulo, which is it's just going to divide this value by another value and then give you the remainder, is what modulo does. So if I do modulo duration, and I can actually write this out very quickly to an attribute. It's equal to circ. Just so you can see what this is doing. See, it's 27 right now, 29, 30, so 33, 34, 35, and 30. At 35, it actually goes back to 0, right? So this is fine, but I actually would like it to be 35 at 35, and then go to 1 on the next frame. So what I like to do is just put frame in parentheses and subtract 1 from it. And then I like to add 1 onto the entire thing. And so what this will do is on the first frame, it will be frame 1 and be at the start of the animation. So like 35, you can see the value right now. It's at 35 and the next one is 1, right? So it's kind of more, to me, more understandable and predictable if you do that. It's not, required by any means, but, go ahead if you want to. Okay, I'm gonna get rid of that attribute now. What we want to do is fit this into a range between 0 and 2 pi, right? So we're going to say circ is equal to, we're going to fit it between, let's see, fit circ between 1, which is the first value that comes up. For you, if you're not doing the -1 + 1 thing, it will be 0, but for me, it's 1. And we're going to fit it between 1 and the duration, and fit it between 0 and 2 pi. All right, so now we have a value, and I shouldn't have gotten rid of that attribute down there. You see this value now is going from 0 all the way up to 2 pi, which is like 6.28, I think, 6.28. Yeah, so that's 6.28 at frame 35, and then on the next frame it starts over, right? So if you were to map this to a circle, like this is your theta value, right? So if you were to map this going all around the circle, then to frame 35 is going to start over and keep going around and around and around, right? Okay. So that's pretty cool. At this point, we need to make a u value. So float u. And how do we get this value? How do we use that value? How is it applicable to us, right? So each of these points has its own theta value, and we need to take that theta and say, okay, how far away from this theta value is the theta value of this circle value that's animating and moving around, right? So how do we do that? We're going to say u is equal to the absolute value of f at theta minus the circ value, right? And this is finding the difference, or because we're taking the absolute value, this is like the distance where it doesn't have a direction. It's the distance. So if we have, as a matter of fact, let me write this out so that you can see this better. So I'm going to just write it out to the color. It's equal to u, right? I'm going to play this. You can see the value moving around now. This point right here, so if I take the difference between this point's theta value and then the actual value that we have spinning around, it will be +1 this way, but -1 this way, unless we take the absolute value where the distance, to both of these points is just 1, so it's the same, it's mirrored. We're going to change that later on, but we do need to know the distance that this spinning value is from the theta value of each of these points, if that makes any sense. Okay, so at this point we do need to fit that value, because right now it's, if I look at our color here, these are values above 1. This isn't very useful to us, so we need to say u is equal to fit, and we're going to fit u between, at the moment, our minimum is 0 because we're taking the absolute value, but that will change later. And we're going to fit it between a float attribute called max dist, and this is the maximum distance away from our spinning point it can be. I'm going to make a parameter for this. Max dist. Okay, so from u, so we're gonna fit u from 0 to max dist between 0 and 1. Okay? This is going to be more useful to us. And right now, max dist is actually equal to 0, so we're going to bump that up. This value will be can be between 0 and 2 pi. So if you want to make this a little bit neater, you can go to the attributes here and change the range to 6.28, right? Accept. There we go. So like if this will be the full circle, you get this like ramp all the way to 6.28, but that's how that works. Okay, so this is all fine and dandy. However, we have an issue. If you haven't noticed, as this circle gets over here, it jumps. There's a pop. It doesn't loop perfectly. And why is that? Well, if we're finding the distance between each of these points' theta values and the theta value that's spinning around, this theta value down here will be closer to 2 pi, but this theta value will be closer to 0. So the distance that this value is from this point's value is all the way around the circle. It can't see right here because this is going to 0 and then jumping to 2 pi. It can't, it's not using the position, like the position attribute. So what we need to do is say, we need to find the minimum distance between the regular way to check and the distance between this point's theta value and this point's and the moving theta value if it were to continue on. So like if I were to go in this direction from this point, then it should be going negative, right? So it's going to be going down to 0 and then negative, right? So these points should all have a negative theta value. And these points, because if we were going to continue this direction, they should be above 2 pi, right? So we need to give all of these points a value that is like increasing above 2 pi. So if this were to continue on this way, or if it were to continue on this way, we need to make sure they have like it's like an upside down dimension value, right? And what we'll just need to do is check the minimum distance between the regular way to find it and this like opposite dimension way to find it, if that makes sense. Opposite dimension does not mean anything. It's just me saying like what would happen in like this alternate way of thinking about the circle, right? So to do that, we're going to create a new float value. We'll call it circ mod, and this is going to be equal to something. What we're going to use here is something interesting. You may not have used it if you are used to VEX, but it is in there. It's the question mark operator. And what this will do is it's kind of like an if statement where it will check if you give it a condition, it will check if that condition is true or false. If it is true, it will take the value before the colon. And if it is false, it'll take the value after the colon, right? So what we can do with this statement here is we can say, okay, if your theta value is less than pi, then you need to be increasing above 2 pi. But if your theta value is greater than pi, because pi is over here on the circle, your theta value needs to be decreasing from 0, right? So how do we do that? So we're just going to say, if the moving value, right, is greater than pi, right, we're going to set this value equal to the value minus 2 pi. Oh, I mistyped. Pi. Right? So that's what's going to happen if your value is greater than pi. But if your value that's spinning around is less than pi, we're going to set this equal to the value plus 2 pi. Is this working? 2 pi. Yeah, okay. Perfect. Cool. And so now what this u value can be is we can say, take the minimum between our regular check, right? I'm going to copy this. The minimum between our regular check and our alternate take check, right? Oh, my apologies. And what this will do is have our value working normally, right? So now that just looks like a loading screen for YouTube or something, which is kind of pissing me off. But no, it's a cool animation and it's animated, so we actually have it all working now, which is very cool. However, something that I did for this pineapple thing, if you notice, is these points, as this moving value is coming in, the pineapples are shooting up quickly, but then as it moves out, they go down slowly, right? So I'm actually manipulating this value differently based on whether the value is coming into the point or going out of the point. And because we've taken the absolute value, we actually can't do that. So how do we get like a range kind of over this whole, like, going from 0 to 1 past the point? How do we do that? Well, what we're going to do here is we actually need to make an if statement, because we need this distance to check, we need to check which method of finding the distance we need to use, but we actually don't need the distance itself. We need a directional number, right? We need like positive or negative. We don't want the actual distance, but we do need the distance to check, how far away it is. So we have to keep this little expression here. And we're going to say, I'm going to close this if statement out. We're going to say if this entire thing is equal to this first argument, right? So that's saying like if what you find to be the minimum is the regular way of checking, then we're just going to set u equal to just this, right? Instead of taking the absolute value. And then I'm going to say else, else we're going to set it to the alternate way of finding theta. Cool. And so now what we have, and so once we do this also, because we're going from like a negative value to a positive value, our lowest value is no longer 0 down here in this fit. And so what we need to do is just do negative max dist. And that'll give us like a range. Oh, okay. I was wondering what was wrong with it, and it is because I did not set u equal to this. So there we go. Now we have it. All right. So, and this looks like it's popping. There's a little bit of a gradient over here, right? But and then it pops right here. But that's actually there's nothing wrong with that. So what that is just doing is giving you that full range, right? So that's very, very helpful. What we can do at this point is just remap u. So we're going to say u is equal to this ramp parameter, right? Remap u. And I'm going to put it in here and make it all monotone cubic and do this shape down to 0 down here. Now, check this out. We're able to mess with the full range of the values, which is super, super, super cool. And we can use this for so many things. What we're going to do with it is mess with the position and rotation, right? So what I'm going to do here is, instead of setting the color, I'm going to create a new vector. I'm actually going to say, let's say this is calc u up there, right? But this down here, we're going to be set position. So we're a vector. We're going to call this vector out. And what we just want to calculate is the vector pointing outwards from these points, but disregarding like the z. You don't have to disregard the z. You can do this normally, but I'd like to disregard the z because if I were to move this circle around, but like keep it on the plane, I don't want to have to mess with or account for the z value. So I'm going to say set at p.x, at p.y, and then the z value will be 0. And we're going to subtract a 0 vector from that. And to see what this is doing, I can set it equal to the normal. And I'm also going to normalize this to get the vector to have a length of 1. And we should be able to see it now. Yeah, so you can see the normals are all pointing straight out, which is exactly what we want. And we're going to use this. We can add this vector to the position to move these points out, right? So we can say, we can get a new vector called new pause, and this will be equal to the current position plus the out vector times a parameter that I'm going to make to control how far out it's going to go. So we'll say pause amount, I don't know, just something. Close that out. And then to visualize this, we're going to do v at p is equal to new pause. And we're going to make this value down here. So you can see a value of 0 would mean it's not adding anything, but if we increase this, it's just going to push the points outwards in the direction of the vector, right? So do a little bit there. And what we want to do now is lerp, right, linear interpolation between the original position and the new position using that U bias value that we've just created. So how do we do that? So we're going to say lerp, it's a function, v at p, new position, and U. And check this out. So this is actually backwards from what my pineapples are doing. This looks very cool. I kind of like this actually, but I did forget to mention that when in this fit, if you reverse 1 and 0, then the leading value, if it's moving in that direction around counterclockwise around the circle, then it will be 0 to 1. But right now it's 1 to 0. So there. So this is what I have the pineapples doing. This is a bit more accurate. I'm going to decrease this distance a little bit so they kind of settle quicker. Yeah. So very cool. We have a neat little animation right now, right? And we can actually go ahead and copy the pineapples to this, right? So copy some pineapples to these points, right? Here we go. Oh my lord, turn the vectors off. Okay. So we got pineapples, but they are not oriented in a good way, right? We need to orient them. And the orient attribute is something that I struggled with for a long time, but I think that I finally get it now after reading lots of CG Wiki articles or pages, I guess. But let's go ahead and orient these pineapples correctly, right? So if you look at the pineapple, and this will be different, for what your model is, but for me, I wanted the pineapples to be oriented like outwards, like this. And if we look at the pineapple, it is, you can think about this as like a line or like a vector. If this was a vector, it would be 0, 1, 0, right? Because it's going straight up on the y-axis. So we want to figure out how we can rotate this pineapple onto our out vector, right? So how do we do that? We're going to create a new point wrangle. We're going to call this init orient for initial orient, right? We're going to say, we're going to actually copy over our out vector stuff because we need that. So we need this line, create our out vector. We want to figure out how to rotate an up vector, 0, 1, 0, onto all of our out vectors that are coming out of our points, right? I'm going to disable the animation for right now. So how do we do that? So we need a vector4 attribute, right? And we're going to call this orient. And we are going to set this equal to the dihedral, right? Dihedral is a function that Houdini gives you that will calculate either a matrix or a quaternion, or a quaternion that will rotate one vector onto another vector, right? So we want to rotate our, up vector onto our out vector, and I'm going to set orient equal to that. So the way to set a vector4 attribute is p at orient. And orient is an attribute that Houdini recognizes and the copy to points node will recognize. Set this equal to our orient here. See, we have our pineapples all oriented correctly. That's awesome. But how do we make them spin? Well, what we can do is create another quaternion here. We'll call it rot for rotation. And this will be equal to the quaternion function. And this is going to calculate a quaternion if you give it an angle and an axis, right? And the angle is in radians and not in degrees. So what I'm going to do here is do our little radians function to convert from degrees. I'm going to do $sign, or actually I'm going to do at frame. So this is the frame attribute times 5. Give it some rotation. And then our axis is going to be our out axis. Okay? And then to combine these, you need to say orient is equal to q multiply. And so if you multiply two quaternions together, you kind of retain the rotation attributes of each. It's kind of funky. I'm sure there's math out there that explains it, but we're just dealing with VEX functions, so we don't need to worry about that. But yeah, so we can multiply, and with q multiply, actually the order in which you provide the quaternions matters. And so I can't remember which one it is, but I think it's rot and then orient comes second, I guess, if you want to do the rotation. Yes, that was correct. Okay, so we can see right now we have our pineapples rotating, right, over time as time increases, and they're all pointing the right way, or the right way. So that's perfect. Awesome. We can add in the animation if we want. But if you look at my original animation, I actually have it so that when they jump up, they're given like a spin velocity, right? Like they start spinning faster and then they kind of slow down. And then when it comes back around, they go spin and stuff, you know. So the way to do that is you have to use a solver because you are basing what it is doing on the last frame. So I'm actually going to clear out this right here and just give it a value of 0. And then I'm going to create a solver to evaluate what's going on, you know, each frame. Plug that in. I'm going to take our orient thing and copy it, and I'm going to put it in the solver. Okay. So what do we need here? So in this solver, it's not going to respect like the animation that you already have. So you need to copy those attributes into the solver. So I'm gonna do attribute copy here and copy what's coming in on the first input. And I want to copy the position. So we keep the animation. And I also would like to copy the U value because that's animating as well. And as a matter of fact, I just realized that I have forgotten to export the U value. So go back to your animation node here. I'm just gonna say f at U value is equal to U. So we have an animating attribute now. Cool. So yeah, so just any like animated attributes, especially position, stuff like that, you know, you want to copy into your simulation here. But okay, so we want to create 2 new attributes here to make these pineapples spin. We're going to create a rotation attribute. It's just going to be like a float. It's going to be like an angle. And we want this to accumulate over time. So it's going to add a value onto the value that this attribute was on the last frame. So it's just going to accumulate over the frame range, right? So we're going to add another attribute called f at spin, and spin is going to be the amount per frame and per point for that matter that we're going to add to the rotation attribute, right? And then in radians we can go in here and already, you know, put in f at rot, right? This is gonna be how much it's gonna rotate. Cool. So now we need another point wrangle, and this is gonna be very, very simple. We just want to calculate the spin here. What spin is going to be plus equals to the U value, right? So, you know, if the U value is 0, it's going to be adding nothing to it. So we are not going to be adding any new rotations on that frame. But if the U value is 1, then we are going to add rotations on that frame, right? And we're going to multiply this by a parameter. I'm going to call it the spin velocity. Cool. And then what we can do also is we want this the amount of spin to decrease over time. So I'm going to say spin is equal to, or sorry, times equal to another parameter called spin drag. And this is going to be how much energy it kind of, or I guess amount of spin that it retains each substep. So if I make these parameters, I'm gonna give it a velocity of 5, so it's gonna be like 1, or yeah, 5 is fine. Like, so this is gonna be like as the u value comes around, it's gonna be a value of 5 that's added to it. But then as time goes on, the drag amount, it will retain it's going to retain 90% of the energy. So each frame, it's going to retain 90%, 90%, and that'll keep decreasing until it gets more, more spin added onto it as that value comes back around. I actually want to decrease this a little bit. Okay. So now I'm going to reset the simulation here. We should be able to watch this. And it is all working correctly. Check this out. So we have the value, comes around, makes them spin, they slow down. Very cool. Very, very, very cool. And what's cool about this solver also is if I reset the simulation, gets rid of it, and click over here, look, it's already cached all the frames because that solver is doing practically no work. So this is very, very lightweight. But very customizable, very procedural. If I were to come over here to the circle and change the number of pineapples that I wanted, so say we have 5 now, works. We can change the speed of the animation, up here with the duration, we can say 15. That's way quicker. You can change all of this stuff. It's all very, very, very customizable. I want this to be slower though. But yeah, very, very, very cool. Make not divisions, sorry. There we go. It is divisions. So yeah, the other thing to be aware of is just there is a solver down here, so it can do some goofy things. So just make sure to be on the first frame or reset the simulation or anything if you see any issues. But this is very, very cool. And then after this, I pretty much just rendered it in Solaris. So put a background on it. There you go. But yeah. So yeah, this stuff that we did right here is very specific to this shot and this kind of radial motion graphics animation. But the polar coordinates tip I think is very applicable to all sorts of things, and I hope it's useful to you in some way. But yeah, I hope you enjoyed this video. I had a lot of fun making it. Let me know if you want to see anything else, and thank you very much for watching. Please like and subscribe, and I'll see you next time.